We are now starting Chapter 16. Chapter 16 is the first chapter for the content for the third exam. And so Chapter 16 is, Chapter 16, things get a little bit more challenging. So kind of make sure you keep up on this. So we'll start here with acids and bases, which is the whole point of Chapter 16 is looking at acids and bases. We're going to start with definitions for acids and bases. To do that, I'm going to show you a Venn diagram of the acid universe, as I like to call it. This is all the things that you could call an acid would fit in this big oval, this big red oval. There is a subset of those things that we would refer to as Arrhenius acids. Most of the things that you would think of when you hear the word acid would be Arrhenius acids. Arrhenius acids, like I said, pretty much anything, hydrochloric acid, acetic acid, formic acid, citric acid, any of the things that you normally think of as acids are typically Arrhenius acids. Our definition for Arrhenius acids is anything that when we put it into water, it increases the concentration of the hydrogen ion. So things that increase concentration of hydrogen ion when you put them into water. Now, there is a bigger category of acids that we like to use that is called Bronsted-Lowry acids. Bronsted-Lowry acids, it gets rid of the definition, it gets rid of the need to have water in the definition. Bronsted-Lowry acids are simply things that donate H plus to other things. So it donates H plus. We will find things that we wouldn't normally think of as acids fit into the Bronsted-Lowry acid definition. Next, we want to look at our third definition of acids, which is called Lewis acids. Now, we will talk about Lewis acids in more detail at the end of the chapter, but Lewis acids are things that are electron pair acceptors. Like I said, we'll get into that in more detail at the end of the chapter, but it gets rid of the need to have hydrogen involved at all. And it's a much broader definition of acids. So in most of this chapter, we're going to focus on the Arrhenius and Bronsted-Lowry definitions. Now, from the first semester of chemistry, I'm sure you guys learned the difference between something that is a strong acid versus something that is a weak acid. But we will look at it in more detail here. Strong acids are things that when we put them into water, they dissociate approximately 100%. Now, they don't literally dissociate 100%, but it's such a high percentage that you might as well call it 100%. 99.99, it dissociates almost 100%. For example, hydrochloric acid is one of our examples of a strong acid. HCl, you put it into water, and essentially 100% of the hydrogen chloride molecules will dissociate to give you hydrogen ion and chloride ion. Conversely, weak acids dissociate somewhat less than 100%. An example of this would be hydrofluoric acid. Hydrofluoric acid, when we put it when we put it into water, we'll get the hydrogen ion and the fluoride ion, but you notice that we use an equilibrium arrow instead of just the regular arrow. We will find a typical solution for HF is going to dissociate about 5%. Now, this will be a concentration dependent number, so that could change depending on concentration. We're going to talk about weak acids in a lot more detail in a later section, section 16.6 in this lecture. Okay, during the first semester, I taught you, or somebody taught you, that there were 7 strong acids. And these are the 7 strong acids. You do need to have these memorized: hydrochloric acid, hydrobromic acid, hydroiodic acid. Those are easy because they're all in group 7. The only one in group 7 that's not strong is HF. We also have nitric acid, chloric acid, perchloric acid, and sulfuric acid. These are all considered strong acids, and they dissociate essentially 100% when we put them into water. Like I said, I want you to memorize these. There are 7 of these strong acids, and there are thousands and thousands of weak acids. It's so much easier just to remember these 7 strong acids. Now, I'm going to give you a little disclaimer here. If you take organic chemistry, which, why wouldn't you, right? All right, if you decide to take organic chemistry, I will tell you about some other acids that are related to sulfuric acid that are considered strong acids. We don't include them in this list because they're not quite as soluble in water, but they are definitely strong acids. So, but for purposes of this class, memorize this list. Now, one more distinction I want to make is the difference between H plus and hydronium. And the difference is just the way it's written, that's all. So if we look at hydrochloric acid, we will see that hydrochloric acid, it can dissociate. It'll give hydrogen ion and chloride ion, and this is a completely legitimate way to write the dissociation of this strong acid. Well, we can also indicate this using water. So we'll say hydrochloric acid plus water gives us hydronium plus chloride. Well, here's the thing. If you have H plus and it has the word AQ by it, that means that that H plus is solvated by the water molecule. And if it's solvated by the water molecule, it's actually in the form of H3O plus. So this implies hydronium. So the H plus implies hydronium. The only difference is on that second equation, the H2O is written, so we have to write the hydronium. So these equations mean exactly the same thing. It's acceptable to use either one. The H plus is actually in the form of hydronium ion. I prefer to use hydronium. So in all of my examples with acids, I will use water and hydronium, and I'll do that throughout this semester. Our next thing is bases. So we've talked about the definition for acids. We want to look at the definition for bases. So everything that will fit in this oval we can consider a base. Now this is a mostly parallel universe to our acids, but there are things that overlap. There are things that can act as acids and bases, but for the most part it is a parallel universe. There is within this, there is a subset of bases that we call Arrhenius bases. If you remember, Arrhenius acids were things that when we put them into water, they increase the concentration of the hydrogen ion. Well, Arrhenius bases, when we put them into water, they will increase the concentration of hydroxide ion. We generally consider Arrhenius bases to be metal hydroxides that will dissociate to some extent to give us hydroxide ion. So an example of that would be like sodium hydroxide, but any metal hydroxide would technically count as an Arrhenius base. We have a second definition for bases that is in the Bronsted-Lowry definition, and that is the Bronsted-Lowry base. If you remember, a Bronsted-Lowry acid was an H plus donor. Well, a Bronsted-Lowry base is an H plus acceptor. If you have a Bronsted-Lowry acid in a reaction, then necessarily you must have a Bronsted-Lowry base that's there to accept it. We will look at this in a lot more detail here shortly. Next, we want to look at Lewis bases. Lewis acids were electron pair acceptors. Lewis bases are electron pair donors. Again, we're going to talk about this towards the end of the chapter. We'll get into that definition, and we're mostly going to focus on Bronsted-Lowry acids and bases with some discussion of Arrhenius. And again, the big distinction there is Arrhenius, it's in water. And in Bronsted-Lowry, we get rid of the need to talk about hydroxide. It's just H+. Okay, well, like with the strong acids, we also have strong Arrhenius bases. Again, these are metal hydroxides that dissociate 100%. If you took General Chemistry 1, you know these bases already. It's going to be the group 1 hydroxides, including lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium, and cesium hydroxide. So those are all of the group 1 metal hydroxides. Now, you'll notice if you look at the bottom of the periodic table right underneath cesium, you will see the metal francium. We generally don't talk about francium hydroxide. I'm sure it is a strong base. However, it is also very radioactive and would be very dangerous to work with. So we just don't even count it. For our group 2 metal hydroxides, that's going to include calcium, strontium, and barium, which are those bottom 3 in the group 2A. And again, right below there's radium hydroxide. So radium would also be a strong base, but again, it's so radioactive, we're going to ignore it. Okay, now I'm going to show you a periodic table here just real quickly. So here is my periodic table. I'm trying to get the glare away. So you'll notice that here are our group 1 hydroxides, there are group 2 hydroxides, and that all of these other metals, they also form hydroxides, but they are not strong bases. And the reason they're not strong bases is they're just not soluble enough. So they're just not soluble enough to be considered strong bases. So let's go back and look. As I mentioned, you want to have these memorized. So make sure you've got those memorized. There are weak Arrhenius bases. These are going to be those other metal hydroxides that I mentioned, and they are just not soluble enough to be considered strong bases. From group 2, magnesium hydroxide is a great example of this. Magnesium hydroxide, when you put it into water, it doesn't dissolve very well. Only about 96 milligrams of magnesium hydroxide will dissolve in pure water, 1 liter of pure water at room temperature. And so we consider magnesium hydroxide to be a weak Arrhenius base. We're going to talk more about this in chapter 17, and it's actually in the second half of chapter 17. So there's a very interesting section on that. In case you're wondering, magnesium hydroxide is milk of magnesia, which you can take if things are, stopped up a little bit and you need to get things moving. Milk of magnesia will help you out. And so it acts as a laxative. Over here, I've got an image of what the milk of magnesia looks like. It looks like milk, except it's much thicker. It's much more viscous than typical milk would be. But it seems kind of funny to have milk of magnesia in a shot glass like that. But oh well. So we're going to talk about that in more detail later. We also want to look at what we refer to as weak nitrogen bases. These are things like ammonia. When we put them into water, they will dissociate to some extent to give us ammonium ion. In this case, ammonia will give us ammonium ion and hydroxide ion. Since it produces hydroxide ion, we consider this a base. So it is a basic solution. For ammonia, at a typical solution of ammonia would only include about 1% of the molecules would be dissociated. 99% of the molecules would still be in the form of the ammonia molecule. So we're going to talk about this in more detail later in this chapter in section 7. In case you're wondering, chapter 16 is a long chapter. Oh, and by the way, ammonia is something that you're likely to have around the house. This is just household ammonia that you use for cleaning. Very, very handy cleaning agent, although be very, very careful with it. It does smell very bad, and of course, you never want to mix ammonia with bleach. In fact, here's a good rule. Don't mix bleach with anything. Yeah. So, public service announcement there. Okay, so now dissociation of ammonia. So the dissociation of ammonia. So here water reacts with the ammonia molecule. You'll see that one of the hydrogens is donated from water. So since water is donating it, water is acting as a Bronsted-Lowry acid in this case. Ammonia is accepting H plus from the water, so ammonia is acting as the Bronsted-Lowry base. So it's H plus acceptor, Bronsted-Lowry base, water, H plus donor. It is a Bronsted-Lowry acid. We'll find that water is amphiprotic, and the prefix amphi, as you're probably familiar with, like an amphibian can live on both land and water. So amphibians, they can live on both. Like an amphitheater is both inside and outside. So part of it's inside, part of it's outside. So it's both. Well, amphi means, amphiprotic means it's both an acid and a base. So water is amphiprotic. Here in the case we saw earlier with hydrochloric acid, water was acting as a base. And so it was accepting H plus. All right. In the case with ammonia that we saw just a minute ago, water was acting as the Bronsted-Lowry acid. It was donating H plus, and ammonia was acting as the base. So water is amphiprotic. It can act as both. All right, we want to look at conjugate acids and bases. Whenever you have an acid that donates H plus to something, what's left over after it's donated H plus, we refer to as the conjugate base. All right, and then whatever the base is, it accepts H plus, and whatever you get after you add H plus to that base is considered the conjugate acid. We're going to look at a few of these examples on the next page, and then we're going to do number 17 on the in-class assignment. So, identifying conjugate acids and bases. The key to doing this is just look at the acid and remove H plus from it. And since you're removing H plus, the charge is going to decrease by 1 or increase by -1 if you want to think of it that way. So you'll remove hydrogen, so you'll get F, but since we're removing H plus, you actually get F minus. So you get F minus, and that's the fluoride ion. For HCl, this one's very similar. So you remove H, you will get Cl minus, the chloride ion. This is acetic acid, and if you remove that hydrogen, you will get the acetate ion, which is just C2H3O2 -1. With sulfuric acid, now sometimes people will make a mistake on this one. They'll try to remove both hydrogens at once. We do not want to do that. We're going to remove just one of those hydrogens, and when we do, we will get HSO4 minus. HSO4 minus is actually still a pretty good acid, and if you remove the H from it, H plus from it, you will get sulfate, SO4 2 minus. For hydronium, hydronium is it is an acid. If you remove H plus from it, you will get water. Water, if you remove H plus from it, you will get hydroxide. Hydroxide still has a hydrogen. If you remove H plus from it, you will get O2 minus. So you'll have a -2 charge on that oxygen. CH4, that's methane. In no reasonable situation would you consider methane to be an acid. In fact, the only reason we care about CH4 as an acid is because of its conjugate base. CH4 is a lousy acid. In fact, if you had an entire solar system full of CH4, you might have a couple of molecules of CH3 minus. That's how weak of an acid it is. It just doesn't dissociate very much. HA, this is a generic designation for an acid. So if you remove the H plus, you'll have A minus. A minus, of course, is not anything in particular. It's just a generic way of representing. Now, for bases and their conjugate acids, you just go the other way. You're going to add hydrogen to it and increase the charge by +1. So if you start off with something negative, it'll increase by +1. Since this is -1, you'll end up with something neutral. If you start off with something neutral, you'll end up with something positive. So NH2 minus, when you add H plus to it, you will get NH3. NH3, if you add H plus to it, you will get NH4 plus. Here is the oxalate ion, so C2O4 2 minus. If you add H plus to it, you'll get HC2O4 -1. Cyanide ion, so Cn minus, you add H plus to it, you'll get the hydrocyanic acid molecule. Both of those are really dangerous. Don't mess with those. All right, nitrate, if you add H plus to it, you will get nitric acid. Nitric acid, normally you wouldn't consider it a base at all, but under very specific conditions, and we actually do this in organic chemistry, it's kind of fun, you can add H plus to it and you'll get H2NO3 plus. Turns out that's really unstable and it breaks apart into some new molecules. If you're interested, take organic chemistry. Okay, so next we've got SH minus. SH minus, you add hydrogen to it, you'll get H2S. So hydrosulfuric acid, H2S. That H2S, that's the smell of rotten eggs. If you've ever smelled rotten eggs, you've smelled H2S. All right, hydroxide, of course, if you add H plus to it, you'll get water. Nitrite, if you add H plus to it, you will get nitrous acid. And then finally, HPO4 2 minus, if you add a hydrogen to it, you're only going to add 1. So the charge is going to go from -2 to -1. You'll get H2PO4 minus. So let's look at number 17 on the in-class assignment. So I'm going to tab over to number 17 on the in-class assignment. And we've got acid-base reactions. These are Lewis acid, or not Lewis, they're Bronsted-Lowry, Bronsted-Lowry acid-base reactions. And we want to identify what thing is the acid and what thing is the base in each of these reactions. And you also want to identify what the conjugate acid and conjugate base is on the other side. So I'm going to do the first one, and then after that I want you to pause the video and attempt to do B through F on your own, but then I'll go through and do it as soon as you're done with that. All right, so we've got ammonium and cyanide. If you have something that does not have hydrogen in it, it can't be the acid. So that means that this, the NH4 plus, has to be the acid. I'm just going to use the letter A for acid, and for base I'll use the B. And then for conjugate acid I'm going to put Ca, and for conjugate base I will put Cb. So there is our acid. That means cyanide is our base. And then HCN. All right, so if this is our base, we add H plus to it. This is our conjugate acid. And then NH3, we remove H plus from the ammonium. We will get ammonia, and that is our conjugate base. So there is our conjugate base. All right, so this is where I want you to pause the video, and I'm going to set my pen down. I want you to pause the video and attempt to do B through F. Okay, so hopefully you went through and did those. So now I'm going to go through and do these. So here we've got CH3, 3N, and H2O. You have to look at the other side to see what changed. You'll see the CH3 picked up in H plus, so that means that this was our base, which means that water was our acid. CH3, 3NH plus is our conjugate acid of this base, and hydroxide is the conjugate base of water. All right, next we've got HCHO2 and phosphate. Since phosphate doesn't have any hydrogens in it, it can't be a Bronsted-Lowry acid, so it must be the base. So that is the acid. When we look at the other side, you'll see that we've removed H plus from this, and that means this is our conjugate base, and HPO42 minus is our conjugate acid of phosphate ion. HBRO and H2O. So HBRO is, well, we have to look at the other side. You'll see we have hydronium and BRO minus. So to get from here to there, we removed a hydrogen. So that means this is our acid, and water must have been our base. For the hydronium ion, that is, if we add H plus to water, that gives us hydronium. So that is our conjugate acid of water, and then BRO minus, which is hypobromite. That is the conjugate base of hypobromous acid. All right, HSO4 minus, HCO3 minus. Looking at these, unless you're familiar with the strength of the acids, looking at these, you probably wouldn't be able to just right off predict which one is the acid. So you need to look over at the other side of the equation. So here we have HSO4 minus, and we have SO42 minus. The difference here is it's lost a hydrogen, so that means this must have been the acid, and HCO3 minus turns into H2CO3, so this was the base. So sulfate is the conjugate base of this acid, and H2CO3, that is the conjugate acid of that base. All right, finally, we have HSO3 minus and hydronium ion. Here we have H2SO3 and H2O. So from here to here, it picks up H plus. That means this was the base. Hydronium must have been the acid. And then here we've got H2SO3. That is the conjugate acid of this base. And water would be the conjugate base of hydronium ion. Okay, so you need to be able to identify the conjugate acid of any base and the conjugate base of any acid. So now we want to look at the relative strengths of acids and bases. So here, I've got a list of acids. This is by no means a complete list of acids, but it's a list of acids, and they are ordered by strength. With the strongest acids up here at the top, we've got 3 of our 7 strong acids up there, and then we've got some weak acids down here, and things we wouldn't normally consider acids down here. So up here at the top, these are strong acids. And what we want to do is we want to look at acids and their relationship with their conjugate base. For a strong acid, the conjugate base of a strong acid is a negligible base. It is so weak we wouldn't normally consider it a base. So for example, hydrochloric acid, really strong acid, but chloride ion is a very weak base. It's so weak that if we put chloride ion into water, it doesn't have any effect on the pH. Right next to it, we've got HSO4 minus. That's the conjugate base of sulfuric acid. Well, HSO4 minus is such a lousy base, actually still an acid. That's how bad of a base it is. Nitrate is, it's a lousy base. It does not act as a base in water in any normal sense of the word. Now, all the ones here that are below hydronium, this is our cutoff between strong acids and weak acids. So here we've got our weak acids. Weak acids are things that when we put them into water, they will dissociate less than 100%. Well, the conjugate base of a weak acid is a weak base. So I'm going to say that again. The conjugate base of a weak acid is a weak base. Now, let me qualify that. The stronger the weak acid, the weaker its conjugate base. But all of these things in here are weak acids. All of these things in here are weak bases. HSO4 minus among weak acids is pretty strong. SO4 minus among weak bases is really weak. All right, so again, the further up this list you go, the stronger the acid. The further up this list you go, the weaker the base. We get down here, HPO4 minus is a pretty lousy acid. It technically is an acid. If you put it into water, it will dissociate a little bit, so it technically is an acid. PO4 minus is its conjugate base, and among weak bases, it's pretty strong. If you have phosphate in a water solution, you will find that that solution will be pretty basic. Now, it won't be a strong base, but it'll be pretty basic. Next, we've got water. Waters are cut off between weak acids and things that we consider negligible acids. They're such lousy acids that we wouldn't call them acids at all. Hydroxide, lousy acid. The conjugate base of a negligible acid is an exceedingly strong base. Very, very strong. These things over here on the right, when we put them into water, 100%. And I'm not even going to qualify that. It's like literally 100% of these will pick up a hydrogen. So, all right. So again, these things are such lousy acids. That means their conjugate bases are extremely strong. So using that list, we can predict the position of equilibrium. So using that list, we can predict the position of equilibrium. And so this is how we do it. If you have a Bronsted-Lowry acid-base reaction, the equilibrium will lie in the opposite direction of the stronger base. So for example, here we've got hydrochloric acid plus water gives us hydronium ion plus chloride ion. Now, I am going to bring up that list. I've got it opened in another document here. I've just got that image file, and so let me go back to this. So we want to identify the base on each side. So HCl is our acid, water is our base. So here is our base. And then hydronium and chloride. Chloride is the conjugate base of HCl. So our bases are water and chloride. And we want to see which one's stronger, water versus chloride. So we'll go back to that list. Here's chloride, there's water. You will see that water is a stronger base than chloride because water is further down this list. All right, since water is a stronger base than chloride, the equilibrium for this reaction will lie to the right. In fact, we will find it lies far to the right. So the equilibrium constant for this will be much, much greater than 1, product favored, to use the terms that we used in chapter 15. So it will be product favored. All right. So now we want to look at this one. So this is acetic acid plus water gives us hydronium and acetate. We want to compare water to acetate. Water is the base here, and acetate is the conjugate base of acetic acid. So water versus acetate. So water versus acetate. We're going to go back to this list. Here's water. And here is acetate. Now, acetate is written in a slightly different way here. It's written as CH3COO minus instead of C2H3O2. Okay, whatever. But you'll see that the acetate is further down the list, meaning that acetate is a stronger base. So since acetate is a stronger base than water, the equilibrium will lie far to the left. So we will find that we will have an equilibrium constant much less than 1. Okay, so now we want to look at number 25, and after we do number 25, that will be the end of our first video. So let's look at number 25. Okay, so Here we want to predict the products. So we want to predict the products, and I'm going to lower this down just a smidge. There we go. All right, so we want to predict the products here. We have O2 minus and H2O. Well, clearly O2 minus has to be the base because water here has to be the acid. The conjugate acid of O2 minus is OH minus. And the conjugate base of H2O is also OH minus. So if we're going to label these, we'd say, all right, this is our base, this is our acid, and it doesn't really matter which one we call conjugate acid and conjugate base. I'm going to call this one conjugate acid and conjugate base, but they're the same thing, right? So they're the same thing. So our bases are O2 minus and hydroxide. So O2 minus and hydroxide. So we're going to go back to that list. All right, so here is the list. And O2 minus versus hydroxide. So you'll see O2 minus is further down than hydroxide. So O2 minus is the stronger base. Since O2 minus is the stronger base, that means the equilibrium for this reaction will lie to the right. So the equilibrium will lie to the right. All right, next, here we've got HC2H3O2. That's acetic acid, and here is HS minus. So on this one, they both have hydrogens that technically could act as acids. So they technically could act as acids. However, we will find that if you're not sure, typically if you've got one that's negative and one that's neutral, and you're not sure which one's the acid is going to be the less negative one. Now, that's not always true, but usually it is. So we'll write the conjugate base of this, which will be C2H3O2 minus AQ. And then for HS minus, its conjugate base would be H2, our conjugate acid would be H2S. And that would be AQ. All right, so again, identifying this is our acid, our base, our conjugate base, and conjugate acid. Our bases are HS minus and acetate. So we're going to go back to that list. So here is our list. Our bases are HS minus and acetate. Here is HS minus. There's acetate. HS minus is a stronger base. So I'm going to put my finger on HS minus. It is a stronger base. All right, HS minus is a stronger base. That means the equilibrium will lie in the opposite direction. In other words, to the right. And then finally on this one, as far as Bronsted-Lowry acid-base reactions go, this one has to be the base because it doesn't have any hydrogens. So we're going to write HNO3. And for water, its conjugate base is hydroxide. All right, so this is our base. That's our acid. Here is our conjugate acid of that base, and hydroxide is the conjugate base of this acid. So now we want to look at our two bases, nitrate versus hydroxide, and see which one is stronger. You probably don't even need to look at this list to do this, but here we go, nitrate versus hydroxide. Well, here's hydroxide down here, pretty strong base. There is nitrate all the way up there, a lousy base. So negligibly base. So there we go. Hydroxide is our stronger base. So we're going to go back to this list. Since hydroxide is the stronger base, the equilibrium here will lie to the left. And pretty significantly to the left. Okay, well, let me make sure. Go back over here. Yes, okay. So we're going to start 16.3 on the next video.